for the opportunity. Thank you for the opportunity
Thank you.
to present my work. In fact, we have a team working on this project for the last few years. And so, yeah, I'm really happy to share what we have learned about this piece of work. But basically, the key idea we try to present here is a solution prediction using machine learning technique for combinatorial optimization. Okay, let's get started. So that just give you a general outline of the what I'm going to cover. First of all, just some general background information, combinatorial optimization, and why machine learning can help in this case. And the key idea is a solution prediction using machine learning. So we're going to use an example, this maximum weight clique problem to illustrate the idea. And hopefully that will be the key message if you can learn tonight, and several other things, as you can see later on. They really just application of this idea to several different scenarios that we deal with in combinatorial optimization. For example, we look at generalization capability of this machine learning model on traveling salesman problem, whether they can generalize on problem instance of different size, or even different category of traveling salesman problem, different characteristic. And that has some really interesting result. And also you see the next one is warm start for ACO. So we use this solution prediction to almost like a seeding or warm starting process. So you can warm start the pheromone matrix in the ACO, and so they can start from a much better position rather than from the scratch. And we also tested on this learning primary heuristic in branch and bound. And finally, the column generation, we showed that we can use this for efficient heuristic pricing in column generation. Okay, so combinatorial optimization. Here are some examples: vehicle routing, beam packing, and timetable scheduling, and airline crew scheduling. So basically, you have a problem. You try to figure out the best combination of its decision variable value, whether it's discrete or real value, and so that it can actually satisfy this. You have a minimization, you have an objective function, define, how good that solution is. Of course, this is subject to a set of constraints. So like the vehicle routing problem, you will look at perhaps the shortest route for shipping all these trucks going, try to get the goods delivered to the destination in a most cost-effective way. Or the beam packing arrangement of this container in an optimal arrangement. So all the time scheduling, right? The exam time scheduling problem where your aim is to let all the students can attend a different exam without having any clash with the timetable. The airline crew scheduling problem that's concerning with the crew member, their availability, or the airplane schedule, and how it can fit all their time available time slot in an optimal fashion and cost effective, for example, right? So there are really everywhere you can see in our society, you can find example of combinatorial optimization. So what are the challenges we're facing? I mean, in the big data era, one particular thing we notice is dimensionality. So they tend to be very large scale, high dimensionality. So we talk about not just few hundred, few thousand, hundreds of thousands, or even millions of variables. So that's, the sheer size of the problem is humongous, right? The problem also often require, the optimization method we're looking at, existing method, often require sort of this handcraft heuristic, which means they tend to be very specific design and ad hoc. So if you have a problem, different problem, and you have to try a different heuristic, right? So the question here is, would it be nice to have some kind of heuristic automatically generated, so that depending on the problem characteristic. The other problem is many of these optimization problem there's a difficulty in formulate in a mathematical explicit manner. So the formulation of the problem play a very important role. Sometimes you need to come up with several different formulation. Picking the right formulation will be more important than just do the search. The other thing we notice is this optimization algorithm tend to be redeveloped from scratch repetitively for different instances of the same problem family, like the traveling salesman, right? You have the problem solved for, like, say, Melbourne CBD area, and sometime later you want to you have to solve them again from scratch. So why can't we learn something from the previously solved instance of this traveling salesman problem and use that to enhance or design our new algorithm for this new problem? So this is where the machine learning can come in and play a role that allow you to learn from historical data, the data you collected from previous solved instance for solving the new instance. So augmentation is enhancing the algorithm development in some way, and automation is, instead of manually specify or set certain parameters, you have to automate it. The process of setting parameter automated. So again, machine learning can play a very important role there. So it's just an example, as I mentioned earlier, right? Traveling salesman is a typical example that people repetitively solve them again and again from scratch. But because we have data these days, abundant of data available, right? We're using sensor technology. So this day we have no shortage of data. Data are sitting there idle, but not actually get used much. So we can think about, we are making use of this data that are already, telling us something about this tour, whether you're delivering a pizza or, but later on you have a tour that is similar. You do not have to start from scratch. You can actually learn from the data, and then somehow using that knowledge, using what you can learn to design a better algorithm, right? So we have plenty of data. This is what we call this problem-specific instance that can be readily collected. The other thing is the maturity of a machine learning and a deep learning technique. They are at this point that is really can have widespread impact. So machine learning these days used everywhere, right? So the key thing is you have the data. If you have the data, then we can try to look at what's underlying the data, what underlying pattern that we can extract from the data. Okay, so here just mention some of this possibility applying machine learning to combinatorial optimization. You can see at the bottom of the slide, Joshua Benjo has this survey paper published in 2021, which have a really good summarization about all the possibility of applying machine learning to combinatorial optimization. I highly recommend you have a read if you want to learn what is possible, research opportunity lying here. And I just give you a few examples here. You can see on the right-hand side, you have a branch and bound, which is a very established mixed integer programming method in the optimization community. And so you have a mixed integer programming problem. You're solving them by first perhaps do a LP relaxation, which is a linear programming relaxation. You solve the linear programming relaxation, but you might have variable that is fractional, because here you're looking for integer solution. Therefore, you have to do some this sort of enumeration, like this x. You have this actual constraint added here. So we call them a flooring. Take the lower integer value, or ceiling. You take the upper level where you get that integer value. So you have then these two children nodes created. Then you just try to solve this LP relaxation at these children nodes, at the child nodes. So if you found the optimal solution, integer one, and you can then, what we call them incumbent, right? So then you can, as you generate other nodes, you solving a more LP relaxation, you compare with this, let's say this upper bound. If it's better, then you replace it. If it's not better than that, then you actually allow you to do some pruning of the tree. So this is how you get this branch and bound search tree generated here. So that's just an example. But quite often you see we face a situation that you have to pick a variable to do the branching and decide which node to expand. So that's a decision-making point for branch and bound method. So how we can do that better? Because currently just using some heuristic, and so machine learning can play a role there, right? The other thing, because I'll continue, so we'll come back to that. We do have an application on this. So the other thing is automatic learning specialized heuristic for different problem instances. So you don't want to have a very specific heuristic only work for one type of problem. So it would be nice to have some way of automatically learning those heuristics from the data. So machine learning can do that, can help you with that. Of course, the key thing is to have some data available, right? The branch and cut is another mathematical programming method where you're required to generate new cut. And current methods tend to generate lots of cut, but in some very inefficient manner. So can we generate this cut, which is a constraint, more intelligently, right? So that's, again, the question that we can ask. So machine learning might be able to play a role here. Or learning by demonstration, this is what really referring to supervised learning. So you have expert, you know the known solution, the optimal solution. Therefore, you can train your model to learn towards that goal with the label data. So the data can have label. In fact, our solution prediction method probably in this category because we use label data. Or you can learn by experience using reinforcement learning. So you gather the data on the fly, you explore, learning by exploring, right? Or you can learn to achieve this automatic parameter tuning instead of manually tuning, right? So automation is a big thing for AI and for machine learning in particular. Okay, here's an example of, in Australia, we have this resource scheduling problem. You can see this picture. The mining company will have to, before they dig this hole, this pits here, they have to drill some holes there and figure out, what's underneath, under the ground, what sort of mineral there. So this is so depends on how you dig, how you excavate. It's a huge optimization, combinatorial optimization problem you're looking at here, because each block, if you design as a variable, there could be several millions of a block. Each block of variable, that means it's several millions of a decision variable we're talking about here. And they are highly constrained because you have to dig, unearth the dirt on the top of level on the surface before you can go deeper, right? So this is a highly constrained. So you can see on the right-hand side, this table, we talk about some large instance of such a problem. They are in the, if the last one is about 3 million variable and 34 million of constraint. They are huge. You cannot even use them directly with this sort of MIP solver that we have available commercially, without considering using some decomposition or problem reduction technique first, right? They just tell you the sheer size of the problem is a very, very significant. So the other example, the traveling salesman problem, we all know, but this is a example. You can see we have 13,000 nodes, but we know the optimal solution. Guess how many, in fact, nodes or edge that used in the optimal solution lies less than 0.01% of all the edge that's out there. So a lot of edge are totally useless. It's not even in the optimal solution. So the problem is very sparse, right? So can we reduce them before we even do optimization? That's the question we want to ask. Similar to the previous one here, right? There are a few millions block or a few millions variable. Can we actually reduce that problem without having to worry? Because some of the block never gets used in your final optimal solution. So here just a typical traveling salesman example again, or something in that category, like an orienteering problem. And so you can see the one on the left-hand side, if you have a complete graph that is every vertex connect, every other vertex, you have lots of edge. But on the right-hand side, after reduction, let's say this is an optimal solution, you really just have a subset of vertex and a very few edge that in your final optimal solution. So the question is, can we do this sort of problem reduction first, right? Because this is a can be significant, the amount of reduction you do. And once this problem reduces much smaller size, and you can just solve the smaller problem, focusing on, now you can apply a solver, for example, right, to solve the problem. And that's essentially you solve the original problem, like you see here. So original problem instance first gets reduced to a much smaller size. Then we can feed that into a typical standard solver. Like you see here, we can use solution methods such as exact method, Cplex, Groupie, widely available, or using heuristic, meta-heuristic like a genetic algorithm, or other local search method. So there are some these sort of problem reduction methods in the literature. Some of them are using the exact approach, but their downside is they're too time consuming, too computationally expensive to use, and not scalable in some way. Advantage is optimality guaranteed, right? They have this optimality guarantee. Whereas the heuristic method, which is in the next category, that is based on greedy rules, they give you approximate solution, but it's so they're really fast. The downside is they do not have optimality guarantee because they are heuristic based. Okay, so this graph here, figure you're looking at here, it just illustrates some of the key idea in terms of what we can do with machine learning for problem reduction. So you can see here, again, using the traveling salesman as example, the yellow edge here, let's say, represent the solved instance of a traveling salesman problem. You already know the solution of that traveling salesman. Now I can construct a training data set for your machine learning model, right? So the training data set will be made up by, in fact, it's edge. So each training instance is edge, right? But I know which edge, whether it belongs to the optimal solution or not. So that's what you see in the middle. That yellow dot is the one that belongs to the optimal solution. Because the problem solved, therefore I know that, right? So you can then try to come up with a machine learning model after doing the training in order to establish its decision boundary, as you see this red straight line, right? To separate these two classes of edge, right? The edge that belong to the optimal solution, the edge that is not belong to optimal solution. So if you can establish that boundary fairly accurate, then I can prune away all these edges that is not appearing in the optimal solution. So once I have learned this model, then I can apply unseen, use an unseen instance and test it. Then I do exactly the same thing. Then I can, of course, the training set I'm talking about, we're using some features define what characterize what that edge is, like different type of attribute. For example, the edge, the cost of the edge, could be some other attribute. All the vertex, we can look at some later on the example. I'm using vertex, but in this case, we use the edge as example. So if you have a set of attributes describing the edge, then you can do that to your unseen example, as you see here as well. So in that feature space, I can then apply that boundary and separate these two set of dots. Then I will consider the edge that on the upper right corner, that will be the one belong to the optimal solution. Suddenly, I can prune away all those edges on the left low quality region, right? So that's what you tend to get. In the end, much prune away, much reduce a search space. So again, problem reduction has been developed by other people, of course, but some of the methods are perhaps tend to be designed using just manually, rely on your intuition, understanding of that particular problem. But in recent time, there's a growing interest in leveraging machine learning to automate the design optimization technique. So we have this, as you see in the previous slide, basically tell you the key idea of how we apply this machine learning for problem reduction. Essentially, you go through this set of steps. So that in plain language, of course, we have pseudocode here. There's more detail in the paper. But first step is to solve a set of easy problem, instance to optimality. Once you have that, you can have label data, constructing your training data set. So I can label decision variable in the traveling salesman case. is the edge, right? It's the edge will be your decision variable, and you can attach a label to that. So this is set the tone for your supervised learning, right? So you know what edge belong to the optimal solution, or what edge do not belong to the optimal solution. Then you just basically try to come up with a set of features defining that decision variable. Let's say the edge, you can have a set of a variable, all the vertex. Then after that, you're really training the model using this supervised learning idea. Because you have a label data, you can do the supervised learning, very typical binary, in fact, classification problem we're talking about here, right? Once the training is done, you can apply that to unseen example, a new graph with vertex, right? Then you can then filter out those edge that you do not predict as belong to the part of optimal solution. Then you have a much smaller problem, right? So that's essentially what you do with this type of machine learning for problem reduction method. So we can use this maximal clique as example. As you see here, this graph on the right-hand side, the maximum clique, maximum weighted clique problem really referring to, you have this graph here, you need to identify a clique is a subset of this vertex, right? So subset of vertex that have the highest, the summation, the weight summation is the maximum. So here in this case, you can see the shaded area. So identify this subset, the vertex 2, 3, and 4 have the highest. If you add this weight together, they have the largest number amount of weight. So that's really the algorithm this formulation, this maximization, trying to do here. You try to identify the maximum weighted clique. So this is a classic problem as well. It have a lot of wide range of application area. I'm not going into detail, but I'm just using it as an example to demonstrate this machine learning for problem reduction idea, right? So if I using just now the vertex as a decision variable, so I try to characterize the vertex, that is the node here. Let's say I just have two features. Very typical, you can have a node degree, or node have a weight, like here you can see the weight there, right? Or have degree, that means how many other nodes is connecting. So if I do that, assuming the problem, this graph that I already solved. So I know what optimal solution is, right? So I know what are this vertex, whether it belongs to the optimal solution or not. So you can see the red dot represent optimal vertex belong to the optimal solution, whereas the gray one, they are not. So the huge imbalance, right? You have a very small minority on this point that belong to the optimal solution, right? So that's what you see. So now I can think about how I can draw a line, right? By calling up a linear function, so that now I can separate these two, right? At least I can capture, hopefully, all the red dots on one side, and the all gray dot, which is those that the vertex do not appear in the optimal solution on the other side. Then I can simply eliminate those are the non-optimal ones, right, under this line, right? So I can achieve sort of reduction here by up to 80%. So there's quite a large reduction already. I can further fine-tune this boundary decision boundary using decision tree, so I can achieve further reduction. That's 88% reduction. Or I can add in more features. So here features, graph-related feature like this node weight, node degree, or some other feature. If you have a MIP a formulation, the objective bound, the other things that mixed integer programming, the cost efficient, number of zeros, non-zero in the constraint matrix, and so on, so forth. But the two features I really want to talk about, that is, I think is play a very important role in our work, is this statistical feature we extracted from random sampling. Random sampling from the generated, this graph that you can identify clique, right? So that's a very important, I guess very important way here as a way of defining new features. So we can use correlation, we can use ranking. So as you see here, if you have a graph you provided to me, I can actually generate the pseudocode provided on the right-hand side. But basically, I can then generate, through this random sampling, generate a set of clique so that they are feasible solution. They're not necessarily the optimal solution, but they have objective value that I can use. So if I have a generate enough random sample, then I can figure out, whether the vertex in this case more frequently appear in the final optimal solution or high quality solution, what we call, right? Not necessarily the final optimal solution, but high quality solution. Then I can figure out, then that feature will be very useful because they establish that kind of a, correlation. If I have this age, I know through this sampling pools, over many samples, I know this frequently appear in the final high quality solution. Therefore, the edge I should perhaps use, right, in future. So if I do that, I can use this ranking-based feature based on that. And also the other one, the correlation-based feature, but also this random sampling, right? So of course, there's not fixed value. You have to do this maybe some player and so on. But the motivation is that we believe all these optimal solutions share some common element, common what we call backbone here in the optimal solution. Therefore, we want to extract out that information through this way of defining statistic feature. That's really the key message. So we can again plot this set of feature. Now more than two feature, you have a multiple feature, but you can project them in a two-dimensional surface by using principal component analysis. You can see we can further reduce substantially, the problem size now down to reduced by 93%, right? So amount of reduction is can be very significant. So here's some data point that you can see on the right hand side, but that generated based on this DMAX library. So that's widely used in scientific research community. So we use 26 graph there. So the number of nodes of some of this graph that ranging from 100 to 1500, or the edge from around 7,000 to 500,000. So very large, some of them. And you can see on this figure that is, in fact, we use not just one figure now. We're using more graph. We're using not just one graph. In the early example, we only say we have a one solved mass clique problem. So one graph, but in fact, you do not have to be confined with using just one graph. You can have a multiple graphs with solved instance, solved solution known. Therefore, you can have label data and you can plot them together here, right? So the other thing we notice is that it's highly imbalanced. So sometimes you have to think about how you deal with imbalanced data by using regularization, using penalty. Yeah, so because what you really want to learn is not missing out those edge or the vertex belong to the optimal solution, but doesn't really matter that much if it's a vertex belong to a non-optimal solution. You can get around that, you can afford to do that, but it's no good if you missed out. If you missing out the edge or the vertex that supposedly belong to the optimal solution, because that's quite serious, right? So these two kind of a class label, you treat them differently. So this is a typical scenario in balanced data, and you have to think about strategy how to deal with that. So here's an example. We set up the experiment and training, right? So we're using this leave one node strategy, which is a typical. So we're using 7 medium-sized graph as training data set, and we reserve the M1 here as test graph, right? Test data set. Remember, in our training data, it's not a graph as a training instance. It's a vertex in this case. It's a training instance. We have a set of attributes defined, as you see early, to describe this vertex, right? So that's represent the instance. So in a sense, there are a lot of these sort of instance in your training data set. For medium-sized data, you can have medium training data set, you can have thousands of instances. But for a large training data set, you contain millions of instances, very large. So we tried a bunch of different machine learning model, but support vector machine is the one that we use most frequently. But you can see, this is just more complex boundary, right? So the red dot is the one that belongs to the optimal solution, whereas the gray one is not, right? So then here just showing some result that we use as to do the problem reduction. So we look at how far we can go with the problem reduction. So we reduce the problem until using this machine learning model until that we cannot, until to the point that we, if you do further reduction, you will detrimental. You won't be able to still capture the optimal solution. So this is as you can see here, the left hand side is on the media graph. So we try machine learning model with different features. So this is FW, which is using only the weight, or using only the degree, node degree, or the bound. The rank is the one that we define as a statistic feature, and the correlation. The last one, ML, is combining all these features together, which is showing perhaps the best performance. So we can reduce the problem down to 27% of the original size, still manage to obtain the optimal solution. Right? So that's on the medium size. But for the large size, you can see the graph is very sparse. So we can reduce them quite significantly, more than 99% for most of them. And then still manage to retain the optimal solution, right? So you see there's a lot of these vertex in the graph are really not appearing in the optimal solution. Therefore, that's why we can do this sort of reduction quite substantially. Yeah. So here showing some of the result. On the we're trying again on these 7 different model using training only on the weight or the degree, the bound or the rank based or the correlation based plus machine learning, combining all of them. So you can see the machine learning one that gets perhaps the best performance. So this is in terms of the objective value, I believe, best objective value. The purple one, that is machine learning model, get the best. So you can see we're using some box plot because there is a stochasticity in the data. We training the 2 features that we get is through this random sampling. So this is why we run the result over 100 runs. Then we take the average. Then you get this sort of distribution. But overall, you can see you can reduce the problem, then still get the best performance in comparison if you're using just some other standard graph feature, right? So the machine learning model definitely does the best. Here it's just showing the x-axis is showing you can do this product reduction. If it's 100%, there's no reduction, right? If you go towards left on the x-axis, you can do some of the reduction and what sort of objective value you can obtain. So we tried on very, very large and hard, difficult graph from this network repository. I think it's a human brain network. They are massive. So then the number of nodes we're talking about is over 500,000 to 600,000. And the number of age is 200 million. So they are massive. Then, but we still just, give a go on our problem reduction method, see how much difference it can make. So this LSCC is really just a local optimized local search method. So we compare the one without reduction, the one with reduction. You can see on all the problem instances, there are 11 different problem instances. They're all showing market improvement in terms of performance. Okay, so now I'm moving on to talk about traveling salesman. So early on, we talked about the maximum clique. So this is back to the traveling salesman problem now. In this paper, we're particularly looking at this generalization capability of our trained machine learning model on, maybe different category of a traveling salesman, easy versus hard, or some other characteristics are slightly different, but they are still traveling salesman problem, right? So this is a really same figure you've seen early on. We go through that process. First, obtain the optimal solved solution for traveling salesman, then define the feature and construct a training set. So then I train the model, they'll learn this decision boundary. Then I can test it on unseen instance, then be able to predict what edge should belong to the optimal solution. That's how we accomplish this problem reduction. Okay, so this is a 5 category of this traveling salesman problem. We got it from this Matilda library. So this is each dot represent a graph. In fact, this is not an edge, right? This is just a problem instance. You can see the distribution of them. So I think the easy and hard really in terms of the type of algorithm can solve or having difficulty in solving them. So the CLK represent a heuristic method. So it's easy for that type of algorithm or hard to that type of algorithm. Or this is another heuristic method, easy and hard. And the last one, you have them random. So they represent some sort of, different category. So what we want to test our method is if we train them on, let's say the CLK easy, can I, observe what they learn? I actually can also predict reasonably well on some other category of traveling salesman problem. So that's exactly what we did here. So we train on the easy graph, then apply them across to the other graph. So there are 5 categories. As you can see, the optimality gap for the easy graph is almost 0 because the blue dot, the optimality gap is almost approaching 0. But they have some difficulty with some other category. But they're still doing pretty good. In average, we talk about the optimality gap is 4.7%, and the amount of reduction we achieved is 93%. The other thing we try to train on hard graph, then see whether you can generalize on other category, including easy and hard graph. And this is same to give us even better result in terms of solution quality. So it's optimality gap reduced to 0.07%. That's why you see all the blue dots, right, approaching to 0. Amount of reduction is not as substantial as the previous one, but you have a better solution quality, right? And we also try on the random graph. So we can train on random graph and test it on all the other category. So this give us some results somewhere in between. You achieve 85% reduction, optimality is 0.4%. So this is interesting, this generalization across different category of TSP problem. The other thing we try is whether we can generalize what we learned on the easy TSP problem on more challenging and larger TSP problem. So we train our model on this random category, randomly generated TSP problem with dimensionality of 100, that's 100 different cities, right? Then once you train that on the same category, you just on the random category, I believe. Then we tested whether it can generalize what they learned on TSP with 200 cities, TSP with 500 up to 2,000 cities, so much larger problem size. And we can see they still managed to generalize really, really well, achieving somewhere between 85 to 90%, approaching 90% reduction, with optimality gap is 0. In fact, with all these problem instance being solved. And interesting because normally, how you have to think about how they actually can generalize across this dimensionality. I guess it's come down to the feature that we design is not bound by this size issue. Therefore, what you learn there is really, I guess, transcend to this size. So that's reviewed in the result here that we observe. So that's I think it's quite significant result. Yeah. So we continue to try our solution prediction method on other type of problem. One thing we tried on this ACO and colony problem, which is normally build a probabilistic model to sample candidate solution, right? And then you over the time iteration steps, then you evolve this pheromone matrix, right? But then now we just see whether we can use machine learning to learn from solved, like say this orienteering problem, which is a variant of TSP, perhaps a combination of TSP combined with knapsack problem. But what you have here is this pheromone matrix, like you see here, represented by this tau or this eta. Eta is also a matrix we call heuristic weight that can be injected with some prior knowledge, and so that you can starting to at a better position. So we just say if we can use machine learning to learn from solve this orienteering tour problem instance, then we can perhaps seed or warm start this either the pheromone matrix or the heuristic weight matrix, right? So again, we repeat the exercise very similar to what we had early on, but of course now the feature the decision problem was the edge with orienteering problem, but the feature reflecting this problem characteristic, right? So I won't go into detail of this first feature, but you can see we, again, using this statistic feature that they define through this random sampling, right? Then we can have a meaningful information that is extracted, that perhaps some idea about that edge, how frequently it appear in the final optimal solution, and using that to train our machine learning model. So these two features, correlation ranking-based feature, gets used again. So this is just very much similar to the stuff I already talked about. You're doing is going through this training stage with this training data set we constructed on, in this case, edge, right? Then when it comes to the test time, you're looking at a new orienteering tool. Again, you just look at using your trend model. You already have this boundary, decision boundary, to make a prediction, which side of boundary it falls. So if you're further away from this boundary in the upper right corner, that means perhaps it's more certain, right, to be that edge appear in the optimal solution. But if you're getting closer to the boundary, perhaps it's less certain, right? So that's why you have a probability around 0.51% for that. We just see here, we just use an example to illustrate. On the other side is those that do not belong to the optimal solution. So again, you can do the pruning or the problem reduction very effectively here. Then we tested on these three different type of seeding or warm start scheme, right? So we replace this eta, which is heuristic weight matrix, with this P model, the probabilistic model we learned from our machine learning model. And we keep the tau, which is the pheromone matrix, intact. This is the original ACO. Or we try, replace this eta with a P, our probability model, multiplied by this Sj divided by Cij. So this is a typical heuristic rule that's used in orienteering problem. I think S is the score at the vertex J, and then C is a cost accumulated from vertex I until vertex J. So this tend to be used in the orienteering problem to start the eta matrix, but we just multiply by our machine learning probabilistic model. And the third one we just replace with the pheromone matrix, right, with this P. Then we can look at the result. Even in the first iteration, you can see there's a marked difference because we're using warm start. So the model already have a very good starting position, even in the first iteration. So this eta hat, which is the second model I'm referring here, that using this multiplication of previous this heuristic rule multiplied by our machine learning probability model, you can get a much better result, much better starting position, even before you continue to learn as usual as an ACO. So the standard ACO is this blue one, is further away from this one, right? So that just shows I guess the warm start that definitely make a huge difference. And here's again, you're showing this different variation of this the different way of doing the warm start. This orange one that's showing again it's eta hat. It's the second variant we try. That definitely showing the best performance right from the beginning. So it can converge really fast, very good, and still maintain that the top place even after quite some time. So we tried two different variants. And also this MMAS, which is a more greedy version of ACO. I think the difference between AS, which is typical standard ACO, and MMAS is that AS is using a population updating your pheromone matrix, which is not as greedy as MMAS because it uses a single global best to update the pheromone matrix. So that's really the difference. So we try them on an even larger problem instance. So again, train on smaller instance, but tested on larger problem instance. You can see the MMAS is the one that get overall the best result. So the difference are significant. We run them average over 100 different instances. And we generalize that. We tested on even real world problem on this tourist trip planning problem. So there are real world data. So the city in Europe. One interesting we did here was that we trained them on synthetic data, then tested on real world, and that's still showing very strong performance. So the other thing that we tried is the primary heuristic, the branch and bound I talked at the start of this talk. The branch and bound trees here, often you have to, think about how you can, you have to decide the variable, which variable to choose to branch, or which node to select in order to do the LP relaxation solving. So sometimes people using heuristic to make those decisions, like you pick the most fractional variable, but it's very sort of a cruel heuristic, right? So that's a little bit, ad hoc. So over the years, in fact, there are a lot of this sort of a heuristic just based on human expert knowledge. You have your understanding of that particular problem, you come up with a heuristic. So this is what we think that machine learning can play a role, because if we have similar type of problem solved already, I can use that, then construct my training data, then train the machine learning model to predict what will be the most likely path to take, right? Whether you make at that particular point, this is the variable I should select, that's the node selection I should go with, right? So that's really the key idea. So because I'm mindful about the time, I won't go into detail, but feel free to have a look at this paper to learn more detail. But here shows the example of 3 variables. Now, once I have a probabilistic model that I have learned, in this case, in fact, we also have to convert that mixed integer formulation instance into some sort of graph, because we're using this graph convolutional network. The input have to be some sort of graph. So the nodes of the graph is a decision variable, which is a variable that we have in the problem formulation. But the edge between the nodes will be indicating there's 2 variables that appear in the same constraint, for example, right? So once you do this transformation into a graph, then you can do all the very similar type of training as I mentioned earlier on, then come up with a probabilistic model, then allow you to define what variable you should take on to do the branching, and what node you should go with in order to do the LP relaxation solving. So here, as this arrow indicates, is a pathway in fact you take. Yeah. So one other thing is this branch and price, but it's still working in the framework of branch and bound. The difference is the branch and price is that at this search tree leaf node, you actually try to solve a very large linear programming problem. So they have so many variables, and you can only perhaps look at a small subset one at a time. So normally people using this Danzig-Wolf reformulation in order to do this column generation to carry out this sort of search. So the column generation really working at this branch and bound leaf nodes. You try to start with a restricted master problem, which is a subset of all the column. But there are so many columns you cannot bring into the research master. So you first solving the research master, that's only give you a feasible solution, but you have a dual solution derived. You can use a dual solution to define what we call pricing problem. So this is what we're interested. We want to say, if I can have a better way of solving the pricing problem, because right now, the pricing problem sometimes can be very challenging to solve, the MLPR. And also you have multiple iterations that you have to go through. Every time when you solve this pricing problem, they give you a column that with negative reduced cost. So that's how we know which column we should enter into the research reduced master problem, so that I can continue to improve reduce restricted master problem. So you're going through many iterations in order to improve this restricted master problem by solving at every iteration this pricing problem. So our focus is whether we can replace this pricing problem by using machine learning prediction to reduce the problem size and solve them more efficiently. So that's what we try to focus on, because we consider that's a bottleneck, right? So here's a pricing problem for graph coloring problem, right? So that's in the literature, you can say Groovy and ACO gets used as the whole range of optimization method get used for solving this sort of a pricing problem. So we want to look at how we can solve them using machine learning, reduce them and solve them more efficiently. So the problem, in fact, is a maximum weight independent set problem, which is a complementary to the to the maximum clique problem we talk about at the early start of the at the early part of the presentation. They are kind of can be converted from one to the other. But again, here we talk about this training and the testing phase. First, constructing training data set. So we look at this pricing problem, which is a maximum independent set problem. So you assuming you solve those instances already available, so you can have a label data. So therefore, you can carry out your supervised learning. Of course, as usual, you have set of feature defined, including our statistically defined feature from the random sampling. So you have a machine learning model learned, and you can then apply that to unseen example, which is this. You have a restricted master problem. Then when they come to the point you're solving this pricing problem here, then you can predict which vertexes belong to the optimal solution or not. Therefore, come up with a reducer problem and solve them very quickly, right? The distinction of what we have here is that we can generate multiple maximum independent set in the usual setting of column generation, right? So if you look at early on, you only have one column that recommended, from solving this pricing problem. You pick the most negative reduced cost column, then add it to the restricted master. But here, because we have this sort of a machine learning based prediction to predict the model based on probabilistic, model that we established, we can actually generate a number of such high quality maximum independent set that can be added to the restricted master problem in one go, even in one iteration. So this is actually quite a difference from the conventional CG process, right? So let's just talk about how we collect those training instances, and how we actually start with different random, different restricted master problem from random column. So therefore give you a rough training instance, right? You actually run some of this CG and in order to collect this optimal solved maximum independent set problem, weighted independent set problem. And that can be used and come back here, right? At that particular CG iteration, and I can decide whether I want to add or, because they have a multiple MLS available now, instead of you have to just pick one and enter into the restricted master problem, you can have a multiple. So you can decide. In the paper actually show we try different strategy, to enter a multiple column, because in literature we realize that sometimes using multiple negative reduced column can actually speed up the whole process. So that's the reason why we do this. So this is definitely showing some of this advantage of our method. So again, we look at the pricing solving. So you can solve more instance, right? Compared with some other method, existing state-of-art method. Or in terms of timing, again, they take a small amount of time. Here on the right, we're showing this, again, small and large graph. So the best objective value in terms of, our pricing method based on machine learning. So our method is winning 52 times out of 81, right? So definitely showing very, very good performance. So that's just a takeaway message, I guess. The key message is this solution prediction using machine learning technique. We believe it's very promising for combinatorial optimization. In particular, apart from the normal graph feature that you can obtain. Now here we're using this sort of feature that derive from statistic information that extracted from some sampling process. And we found it's very, very effective in predicting whether the decision error is part of the optimal solution or not, right? And we demonstrate that this sort of a solution prediction via machine learning can be generally applicable to a variety of situations, as you see in the several examples I have just shown you. So I'm sure there are more can be done. There are more application or different type of scenario you can consider, but that's for future research, right? So this is some of the publication that we have produced in the last 2 years. And these are the people I would like to acknowledge their contribution. To have a team of people working on this project for the last few years. Thank you very much. I guess I use all the time. You're muted.
Oh, thank you very much. I just want to thank you for such an interesting talk. Very interesting. We have time for questions. I think it's mainly depending on Xiaodong's availability. So if you ask a question, I'm going to let you unmute yourself, and I would, encourage you to just talk, because that will be included in the recording rather than, just typing in the chat. So I'm going to let you unmute yourself. Oh, yeah. Okay, so you can just, unmute yourself and talk.
Xiaodong.
Yeah.
Hello, Rahul, how are you?
I can start. Yeah,
so,
fantastic.
Great to see you here.
Yeah, you can see I am different now.
Yeah,
right?
you have some beer. That's different.
Yeah, because I'm a man. Yeah, fantastic. I think a lot of exciting work you are doing. I enjoyed it. Just a simple question.
Yes.
So you mainly discussed about the quality for the reduction and non-reduction problem sizes, right? So if you reduce the dimension, the dimension reduction process is one process, and then the optimization is the second process.
Yes.
So do you have any comparison quality versus the computational time? It's my curiosity. I believe you have done it, but my curiosity that you have significantly reduced, you got good solution at the end, but what about the computational time comparison for these two different approaches?
Generally, I mean, I can show you some early examples. I'm mining example. It's even unsolvable, right? If you do not do any reduction or prediction like this one, right? So problem reduction certainly make it possible to solve the problem by applying a conventional solver. Right? That's why we talk about you first need to do some of this problem reduction. Then it's made it possible to apply some of the solution method. But the type of problem we're looking at, is graph problem, right? All this example I show you can say maximum clique or traveling salesman are graph based. So we're talking about reducing vertex of our edge, right? That is not typically belong to the optimal solution for traveling salesman problem, for orienteering problem, right? So whether that can be translated into some other type of problem, but so far what we have done, even the mixed integer problem, we converted them into graph. Then suddenly everything worked, right? Then I can say how I can do the reduction because I'm just reducing either the edge or the vertex. Then obviously the efficiency will be better and make it possible to solve it, of course. Yeah.
Okay, thank you.
Thank
and
you.
Best wishes for further extension of this work. Yeah, thank you.
Thank you. Yeah.
Thank you, Rahul.
So I can see someone raising hand. Shu Yang.
Hello, Professor Li. It's nice to meet you here. Thanks very much for your interesting talk. So just one thing, if I'm missing, if I don't understand it, is so when you talk about when you apply the problem reduction on the network instances from a network repository. So what properties do you want to retain or do you want to preserve when you do that? Because certainly for that kind of problem, they don't have optimization objectives or objective functions, right?
No, we looking at either edge or the vertex, very typical for graph, right? So either this is DMAC or this is network. What's the other one? And the network, there's another problem, but typically we look at either vertex or edge and look at what sort of attribute we can come up with or feature we can come up with defining those those edge or vertex in a very meaningful way, right? So if you look at the where example, here, okay, so this is orienteering problem, I believe, yeah. So we have some feature defined here, you know, because this is all related to orienteering problem. But I have to say, if you look at very typical TSP, then you have degree, right? Definitely not say how many vertex the current vertex connecting to. That's degree. That's one attribute. The other one, vertex, you might have weight, right? So these are the typical one. But when you have a more kind of a elaborate version, like an orienteering problem, the characteristic about orienteering problem obviously will come into a play, right? When you're designing those features, you have to consider them so that will best capture what's going on there in terms of that attribute, whether it's contributed towards your final predicted outcome, right? But I think what we have found that if you just look at the TSP problem, the feature that it really coming back early, but the node degree or node weight, they are very kind of local type of feature. You look at the current nodes, how many is connected, right? In the vicinity, in the neighborhood, and the weight is a current node that carry how much weight it has, right? But the statistical feature that we define, they're not bound with that. In fact, because you do sampling, you would have this. You have a graph, you know, with a number of vertex. I can use that to generate a lot of subgraph, even, right? And then I can calculate the clique like this. So this is a procedure we use, this random sampling. So if your sampling size is large enough, you can actually derive some information that is very, very important in terms of predicting your final outcome. That is whether that edge supposedly have a high likelihood belonging to a optimal solution. So that's why that's actually reflected in our results as well. So if you're just using this individual feature that is more local type of feature, like FW, FD, they tend to, you know, they perform sometimes not really well, especially when you reduce the size. Like here, the weight, right? The weight here, you can see if you reduce them 40% of the original problem, then they're not really good. Whereas our, that is statistically derived feature, have a much better performance. In terms of even you reduce the problem, you can still capture the optimal solution, right? So it all comes down to specific problem, how you can define those. So that's probably the most difficult or most important part of this whole thing. If I want to figure out this is my decision variable, either edge or vertex, and whether they actually belong to the optimal solution, what sort of a feature I need to come up with, I need to design in order to reflect that really well, right? So that's the important thing.
Okay, thank you. If there is time, I might ask another quick question. So basically, this kind of approach have been proposed in 2016. So since then, I've been following this kind of machine learning-based approaches for MLP. So I already talked to the group lead developers. They don't seem to be willing to integrate this kind of approaches to their softwares or softwares. So what do you think, what are the challenges for them to integrate this kind of approaches to their current platform?
I'm not quite sure which one you're talking about, but from what I know in the literature review, from our literature review, there are in fact still very few papers, not that many. Maybe there are a few work they're doing them in a very implicit manner. So what we do is very explicit. We say we remove the edge if it's not part of the, the optimal solution. Whereas there are a few work that they're doing problem reduction, but still using probability. So they're not kind of exclude the edge completely. So that there's some probability associated with that. So yeah, so maybe you can send me the paper later on afterwards, and I can have a look, and then I can tell you more. Right now, I'm not sure which one.
No, it's all right. It's just a general comments, rather than a question. Yeah. Okay. Thanks very much.
Thank you. I can see there's someone in the chat. There's a question from Zhixing, Huang Zhixing. So it says, have you considered extending this ML data to some surrogate model? Yeah, surrogate model. What we want to apply this sort of model is to, combinatorial optimization, where there's some point of the process, some step of that optimization process require decision making. We want to see whether machine learning can play a role, replacing human heuristic or manually tune, a parameter or specify parameter. Instead, we use machine learning, right, to learn from the historical data, the data you already collect. You can see for our model to work, we have to run this optimization model, assuming we generate optimal solved instance. So that's where I can get the training data, right, the label data, and then I can use that to to construct my learning model, and from there onward, then I can predict, I can replace that the human craft heuristic, right, in the optimization process. Instead of using a human craft heuristic, now I have a machine learning based decision making step, right? So that's really what we try to focus on. So I don't know the surrogate model scenario. Surrogate model most time is about saving computational cost. So that might be a step that you require some decision making. When you do the surrogate modeling, that you can gather data. Then yes, of course, then there's a possibility there. The key thing is to gather data from your solved instance, right? When you have an optimization method, then I can learn something from that. So next time I don't have to start from scratch. So that's really the key difference. Yeah. So you say by this means the well-defined model can be used in the course of search rather than only at the beginning of the search. To reduce the problem, still have a chance to be evaluated in the search, but with bias possibility. So we reduce the problem. So once it's reduced, we just apply the solver to that reduced problem, and that's essentially you solve the original problem. So that's what we believe. The training is really just focused on predicting what edge or vertex can be eliminated. That's really the key task, right? So once it's reduced, you detach from this whole thing. I'm just treating as a new optimization problem, but it's much smaller now, right? Then I can just solve that with standard solution technique. Yeah. Oh, there are some other questions. I don't know, have to read them.
Yeah, that's why I suggest if you directly talk. Yeah.
Someone asking job scheduling problem, give some suggestion how I can make use of the scheduling. But I mentioned is scheduling just another combinatorial problem. So what we have here is a graph problem, right? So if you can turn that into a graph problem, then there's always a possibility. Yes. Right. So yeah, that's something for you to think about. Can you convert it into some kind of equivalent to a graph? Okay.
So does it mean, sorry, can I follow? So does it mean that it has to be worked on graphs?
So at least the problem we have tried so far is on some kind of a graph. Even for them branch and bound, we turn them into a graph, fit into the branch and bound. Fit into that graph neural network machine learning model, right? So for the column generation, the pricing problem, that example I showed, is also a graph. It's a maximum independent set problem, which is a graph. So you see the problem we have tried so far, they are typical graph-based problem. But graph-based problems are everywhere anyway, right? So a lot of the combinatorial are indeed graph-based. So therefore, they do have this widespread, application.
Thank you. We still got some more questions on chat. Fengyang, do you want to talk?
Okay. Hello, Professor
Hello.
Lee. Yeah. So I have small question like, do we have some measurement for to defining a problem instance is easy or hard?
So the example I showed in the traveling salesman, another example that is already developed by this group of people in Melbourne University, which is not far from RMIT, just few city block away. Kate Smith. So if you read that paper, they define this TSP problem. They categorize them into this easy and hard. But they're using some kind of whether a heuristic algorithm, like in this case CLK, can solve them easily or not, as a way of differentiate them. So so you can perhaps have a look at their website and see how they must have some information in terms of how they categorize this. My understanding, they're using heuristic, whether this can be solved by a heuristic method easily or not, and use that as a way of to categorize this some, the so-called easy and hard instance for traveling salesman.
Okay, I see. Okay, so another question is, so
You mentioned dimensionality. I'm reading your
yes,
chat. Yeah.
yes. So a problem instance with lower dimensionality, we can learn some knowledge from that. But how can we apply it to a
Higher dimensionality.
bigger instance or something like that? Because it's a larger input space.
Yeah. That's exactly what we showed here. If you look at here, generalization over different problem size. So we only train them using smaller problem size, like here, 100 dimension, but we tested whether they can predict, on this unseen instance, a traveling salesman instance, but it's much larger dimensionality, like 200 up to 2000 dimensionality. We can still correctly predict, most of the time, and accomplish that problem reduction. So you probably wonder why, because this work in fact is quite unique, I would say, right? Because a lot of people in the past they kind of thinking about generalization, but it's same size. You cannot copy out. I think it has a lot to do with type of feature you define. If the type of feature you define here is not bound by some of these things that are associated with the problem size, then you learn something that is beyond the restriction just on the size of the problem. So we use a local feature, like those edge weight or degree, but we have this statistic feature, statistically derived feature that is doing this random sampling. We think that also is a very important a feature to use. So we have two features in fact here, right? So this is correlation based and ranking based, and not, at least through our experimental result, we demonstrate it doesn't have this issue with. I wouldn't say there's no issue at all with dimensionality as you go harder, but at least for up to this 2000 dimension for this randomly generated TSP problem, we can demonstrate they can still carry out problem reduction quite nicely, because up to 85% reduction or up to almost 90%, right? 85 to 90%, right? So you still get the optimal solution in the end.
Okay, so we need such kind of features that has very minimum effect on the dimensionality. So even
correct,
no
because
matter how
you can see the way we use feature.
Yeah.
The way we define feature is not where we say, it's kind of a tied with a specific dimensionality, right? So even it's randomly generated random sampling process, we generate a feature. So I think that's really the key thing that maybe I think play a central role in all this our work. That is this part. So maybe you read our paper and have a more close look and how this, you can try it out. We do have the source code available, and you can try it out, because we use this not just for you know, when you construct your training set, when you come to prediction of unseen instance, you still need to go through this this sort of stochastic, you know, sampling process to be able to define that feature for the unseen instance, right? And that's and nowhere in this, you know, this feature that you can see that is bound to this dimensionality. So in that sense, you know, what you learn maybe is transcend to the size issue.
Yeah, sure. Thank you. Thank you.
All right, cool.
Yeah. The next one I think is Yun Zhuang.
Oh, Yun Zhuang, our student.
Oh, Yun Zhuang. Okay. Oh, probably it's not a question, it's a comment.
Where is it? I can't tell.
Oh, they said, I guess there must exist some commonalities in small and
Oh, okay, I can see Yun Zhuang talk. Yeah.
你跑这儿了，
我这个
你刚刚不还提问了吗？跑这儿。
So Yun Zhuang said there must be exist some commonality in small and large problems. Yes, exactly. Yeah. So it's transcend the dimensionality issue. So there must be this what we call backbone here, or the commonality is not just problem salesman, you know, only available to the 100 dimension problem, but not the 200 dimension. Obviously, there's something in common across this dimensionality, right? Different dimensionality. That's what looked like. That's what the model managed to learn. Yeah.
Yeah.
But you can see we're also using training on hard instances to then come back to predict the easy problem in some of the experiment that show even better result. But obviously, in most typical situation is that you're most likely to get solved instance for easy problem instance, right? Then you can use that to construct your training data set to predict that is more challenging and difficult problem. So the more challenging and difficult problem, high dimension or whatever, more challenging, they of course they are harder to get optimal instance, optimal solution, right? To start with. But for our approach to work, you have to have solved instance to start with, because that's give you the label of the data and you can construct your training data set, right?
And still got some more questions here. Next one is Davon. Saying how many layers in your CGM model?
Oh, you asking this very detailed. So maybe Yun Zhuang will have some comment on that. Yun Zhuang, because it's a guy who did the GCN model for primary heuristic learning. Yeah. So I don't recall that specific detail, but the reason we're using GCN because we want to train. You know, we have this mixed integer problems, but turn them into a graph so that I can fit into GCN with a graph, because that's what typically you do with GCN. You have a graph problem that you can then start a training process. Yeah.
And next saying how to choose
proper feature. It's not just choose. In fact, you need to define. You need to come up with feature that is reflecting the characteristic of the problem. But you can see I mentioned is some of the feature are local feature. They might not be that effective, and that's why we were, you know, thinking about our type of feature that can be more effective. And then we think about this, you know, this random sampling process is actually quite, I think is one of the unique contribution of our work, right? Transcend, you know, oh, there's a few 4 or 5 different papers. We're all using that statistically derived feature based on random sampling that allow us to identify that decision variable, whether it's have a high correlation to a high likelihood, right, to be part of the optimal solution. So yeah, so I hope maybe you can have a look at our paper, and especially starting that how we define that statistic feature. That's actually quite crucial, because you can get global information, not just local information. When you have a node degree, that's really local information, right? only the node and then in the vicinity of that node, how many vertices connect. So that's degree of the vertex. Or you see a vertex weight, that's only reflecting the weight of that particular vertex, but nothing else, right? So, but this statistically defined information, because you sample over many possible, like say clique, right? It's not necessarily the optimal clique or maximum clique, but it's some kind of feasible solution there. They reflecting, so you can calculate the fitness of them. So once you have that, you know this edge, whether it's happen frequently. If it happen to occur frequently in a high quality solution, they should have higher score, right? So this is what's the key information you try to obtain. That allow you in the future, you can predict an edge or vertex that have a similar feature, right? Similar in terms of the feature that you have defined. Then you can put them in that category. That should definitely also belong to, maybe the optimal solution, right? So that's really the key information. I think this global information sharing is play also a very important role. Yeah.
I think we got the last one.
So Jie was saying, how could one attempt to automate the process, particularly feature selection, even automate the optimal parameter in the solver? Or you cannot automate the feature selection. The feature, no feature selection. I just define the feature in the first place, right? So for machine learning model to work, I mean, we talk about supervised learning here. You have to construct your training data set. To construct the training data set, you have to define the feature first, right? A number of feature that what you're hoping the feature will capture some important information, like high correlation in terms of its predictive power of what the final outcome going to be, right? So that's where in a typical machine learning scenario, the feature you want to pick, right? There are features that is highly correlated to the prediction outcome. There are features less correlated. Therefore, maybe those features are just random noise. We can remove that. But the feature, if you have high correlation to the final prediction outcome, then therefore these are the important features, right? You want to keep, right? But you need to define that feature first in our case here, right? So we have to run this optimization run, generate a lot of this data. Then next thing, which is a crucial step, is to define the feature. Yeah. We not even talk about feature selection, but you could obviously do something like that. But that's a secondary. That's not most important thing, right? The important thing, even just come up with a very few very meaningful feature. That's the I think that's a very crucial step.
Okay, I think we have finished all the questions. I actually have some questions, but probably we can talk offline. It's already half an hour over, and also we still got a lot of audience here. This is a very interesting talk and interactions. So I would like to thank Professor Xiaodong Li again for this very interesting talk, and also thank you for your time. It's already 1 hour and a half to share with us this excellent work. And also, of course, Yuan is also here, and also some other co-authors are here to help answer questions. Thank you very much.
Thank you, Yi. Anyone who would like to, have a chat with me after sending email, no problem. I'll do my best to answer your questions. Thank you.
Yeah, and also we will we are recording, so we will put the recording somewhere, and also we'll send out the announcement when the recording is ready, if you would like to watch later on. So I'm going to stop.